Have you ever just stopped and thought about how incredible sight really is? I mean, how everything you're looking at right now isn't just a flat picture, but this fully formed 3D world you can actually move around in? Well, today, we're going to explore the science behind that everyday miracle. Let's dive in and see how our brains pull off this amazing trick.
So, this is the big question, right? Because the light hitting your retina is, for all intents and purposes, flat. It's basically a photograph. But your brain, in less than a blink of an eye, turns that into this deep, detailed, interactive reality. So how on earth does it manage that?
And this slide really lays out the challenge. The raw data from your eye is flat, it can be pretty ambiguous, and there's honestly not a ton of information there. But the world you actually experience, it has depth, it's got a clear structure, and it's just packed with rich detail. Your brain is basically taking a rough sketch and turning it into a masterpiece in real time.
Okay, so there's a technical name for this. Scientists call it the ill-posed problem. Think of it like this. If you draw a square on a piece of paper, it could be a picture of a perfect cube. Or it could be a picture of a long, weirdly stretched out rectangle that just happens to look like a cube from your exact angle. There are infinite possibilities. So how does your brain pick the right one and get it right almost every single time?
Well, here's the thing. The brain doesn't solve this impossible math problem from scratch. It cheats. It uses a bunch of built-in rules, these, you could call them secret shortcuts, that have been perfected over millions of years. Let's take a look at a couple of the most important ones.
The first, and maybe the most powerful shortcut, is the symmetry principle. Basically, when your brain sees a 2D shape, it makes a massive bet. It just assumes that the real-world 3D object is symmetrical. You know, when you see a face, you just perceive it as a balanced 3D shape, not some bizarre, warped object seen from a 1 in a million viewpoint. That single assumption wipes out countless wrong answers instantly.
And this isn't just some minor detail. The research calls it the sine qua non of shape perception. That's a fancy Latin phrase that literally means without which, nothing. So it's not just a nice little feature. It is the absolute foundation that our 3D vision is built on.
Next up, we've got the simplicity principle. When faced with a bunch of different 3D shapes that could make the same 2D image, your brain is, well, it's lazy, but in the best possible way. It always picks the simplest, most stable, least complicated answer. It's all about being efficient.
And the brain has a whole playbook full of these rules. It prefers shapes that look realistic, something called veridicality. It hates things that are too complex. It just assumes objects are solid. It uses those Gestalt laws you might have learned about in school to group things together. It's this whole logical system running completely subconsciously, which leads to a pretty cool idea. If our vision is just based on a rulebook, could we teach that same book of rules to a machine?
And that's exactly what researchers are doing. They're effectively trying to reverse engineer human vision. The thinking goes, if the brain uses this set of rules to see, then maybe, just maybe, the key to machine sight is teaching a computer those exact same rules.
The ultimate goal here, as the research makes really clear, isn't just about making a machine that can see. It's about building a model that can see like a human. One that can take that flat 2D picture and build a rich 3D world with the same accuracy that you or I can.
So how's it do it? The process is actually pretty straightforward. First, the machine just analyzes the basic lines and shapes in a 2D image. Then it uses those principles we talked about, symmetry, simplicity, as mathematical rules. And finally, it crunches the numbers to figure out the most probable 3D shape that fits all those rules.
So, just to be crystal clear, we're not just showing the machine a huge library of objects to memorize. We're teaching it the fundamental logic of perception. We're literally giving it the brain's own secret shortcuts.
But what happens when we move beyond just a single static image? Well, by giving the machine more complex data, we can start to unlock some abilities that are, in some ways, even more powerful than our own.
This is where things get really dynamic. You have techniques like stereo vision, which uses two images, just like our two eyes, to calculate depth with incredible precision. And then there's optic flow, which uses motion itself as a clue to figure out an object's 3D shape as it moves.
And on the topic of stereo vision, scientists working on these computer models stumbled onto something completely mind-bending about how it all works.
Take a look at this. The number is 0. That is the amount of information a machine needs about eye movement or muscle feedback to calculate depth from two pictures. 0. It can all be done with pure geometric optics. All the information it needs for 3D vision is already right there in the geometry of the two flat images.
And that just raises a huge question. We've kind of always assumed that the feedback from our eye muscles helps with our own depth perception. But if a machine can do it without any of that, does that mean our own brains are using an even more elegant, purely computational shortcut that we don't even know about yet?
Now, you might be thinking, okay, this is all for self-driving cars and cool robots, and yeah, for sure. But the real implications of this research go so much deeper than that.
The real goal here isn't just engineering, it's fundamental science. By trying to build models that see like humans, we get to test our theories about how our own minds work. It's our best shot at finally understanding the deep why and how of our own perception.
Really? It's like we're building a mirror. Every time we teach a machine one of the brain's secret rules, and it works, that mirror gives us a clearer reflection of the brilliant hidden processes that are happening inside our own heads every moment of every day.
And all of this leaves us with one final, pretty provocative thought to chew on. If we actually succeed, if we teach machines our complete perceptual playbook, all the shortcuts, all the biases, all the rules, will they actually see the world the same way we do? Or will their digital nature lead them to a kind of sight that is totally, fundamentally alien to us? Something to think about.